FreeBSD. It's one of the most reliable operating systems out there, right? A real workhorse. Well, today we're tearing down a major security flaw, CVE-2025-14558, that was found hiding right inside of it. This is a crazy story about misplaced trust and how a single tiny network message could let someone completely hijack a server. Let's just start with a number, 9.8 out of 10. That's not just high, that's basically game over critical. A score like this screams two things. It's super easy for an attacker to pull off, and the damage is absolutely catastrophic. We're talking total system compromise. So that brings us to the big question, right? How in the world can one single network message totally hijack a server? I mean, this is a packet your system is supposed to be listening for. How does that get turned into a weapon? Well, stick around because that's exactly what we're going to break down. All right, so here's our game plan. We'll start with the flaw itself, hiding in plain sight. Then we'll cover how your network is supposed to configure itself, before we get into how the bad guys hijack that process. After that, we'll check out the real-world exploit tools, how you can actually defend your own systems, and wrap up with the big lesson here about trust. Okay, let's dive in. First section, a flaw hiding in plain sight. This is where we properly introduce our vulnerability of the day, CVE-2025-14558. And yeah, it's a textbook example of a huge problem lurking in a place you'd never think to look, a basic, fundamental networking feature. So, what makes up that terrifying 9.8 score? Well, the details are pretty wild. The attacker just needs to be on the same local network as you. Think about that, the person sitting next to you at a coffee shop or anyone on your company's network. The attack is super simple to pull off. And here's the real kicker. It needs 0 privileges and 0 user interaction. No one has to click a bad link, no one has to type a password. Your server just gets owned, silently. All right, so to really get how this all went so wrong, we gotta first understand how it's supposed to work, right? You have to see the blueprints before you can spot the crack in the foundation. So let's look at how your network configures itself automatically. The main character in our story is this thing called Slack. That stands for Stateless Address Auto Configuration. It's a core feature of IPv6, and its whole job is to make life easy. It lets your devices hop on a network and just figure everything out on their own. No messing with settings, no waiting for a DHCP server. It's designed to be completely zero touch. Okay, so here's how the handoff is supposed to go. You've got this little daemon called RT-solved. Think of it as a listener. It's just sitting there waiting for messages from the network router. When a message comes in, RT-solved grabs the important stuff like DNS info. Then it turns around and hands that info to a script called resolveconf. And resolveconf's job is to update the system settings. See? It's a simple, automated little chain of events, and the whole thing works because each part trusts the other. Now, this is absolutely crucial to understand. We've got two key players here, ris-sold and resolveconf, but they are fundamentally different. Ris-sold is a compiled binary program. It's like a gatekeeper that just listens and passes things through. But resolveconf, that's a shell script. It's an orchestrator. It doesn't just hold data, it can execute commands. And here's the flaw. The gatekeeper, ris-sold, blindly trusts everything it hears from the network and just hands it right over to the script that can run commands. You can probably see where this is going. Okay, now for the main event, the attack. This is exactly how that misplaced trust gets turned into a full-on system compromise. So the core of the problem, the absolute heart of it, is unvalidated input. The RTL-sold daemon just doesn't check its work. It gets a packet that says, hey, here's a domain name. And it never, ever stops to ask, wait a minute, is this really a domain name? It just blindly trusts it and passes it on. This is like security 101 stuff, and that failure to validate is the original sin here. And this is the weapon. It looks kind of like a domain name, right? It ends in .com, but look closer. Instead of example.com, the attacker sends this. See that $sign and the parentheses? To you and me, it's just symbols, but to a shell script, that is a magic command. It means whatever is inside these parentheses, don't just read it, run it as a command. And the command inside is ID, a simple little program that just tells you who the current user is. So let's trace the path of this attack, step by step. 1. The attacker broadcasts their specially crafted router message containing that fake domain. 2. Our trusty RTS-sold daemon sees it, doesn't think twice, and passes it along to resolveconf. 3. Now the shell script gets it. It sees the $sign and goes, oh, I'm supposed to execute this, and it runs the ID command. And because these services run with high privileges, that command runs as root. Boom. The output gets written to a file, and the attacker now has proof. They can run any command they want as the most powerful user on the system. It's game over. Now, I want to be super clear. This isn't some theoretical what-if scenario. No way. The moment this vulnerability was made public, the race was on. Security researchers, and you can bet the bad guys too, started building tools to make this attack push-button simple. And look at this. The exploit tools popped up everywhere. We're talking Python scripts on GitHub you could just download and run. But the real game changer was when it got added to the Metasploit framework. If you don't know, Metasploit is basically the Swiss Army knife for hackers and security testers. Once a vulnerability has a Metasploit module, it's no longer just for the experts. It means the attack is now reliable, automated, and available to, well, pretty much anyone. Okay, that's enough doom and gloom. We've seen how the break-in works. Now let's talk about how to lock the doors. What can you actually do to defend your systems against this? The good news is the FreeBSD team jumped on this and pushed out patches really fast. For most people, if you're running a standard install, it's literally just 2 commands. FreeBSD update fetch, then FreeBSD update install. Done. If you're one of those people who builds from source, you know the drill. Grab the patch, recompile. The #1 takeaway here is simple. Go patch your systems, now. But hey, what if you can't patch right this second for some reason? You're not totally out of luck. You've still got options. This is where we talk about defense in depth, right? Multiple layers of security. First off, if you're not even using IPv6 autoconfig, just turn the art sold service off completely. Problem solved. You can also tell your network interfaces to just ignore these specific router messages. But maybe the best workaround is at the network hardware level. A lot of modern switches have a feature called RA guard that can filter and block these malicious packets before they even get close to your servers. All right, so let's pull back from the technical details for a second and look at the bigger picture. Because this one bug, it actually tells us a whole lot about system trust, about security, and frankly, about the messy reality of how software is made. And here's the crazy part. When researchers dug into the source code, they found a comment, a note left by a developer years ago. It was marked with XXX, which in developer speak is basically a giant blinking sign that says, hey, this is broken, we need to fix this. This wasn't some hidden unknown flaw. It was known. It was a piece of technical debt just sitting there, a ticking time bomb waiting to go off. And let's be real, this isn't some brand new, sophisticated kind of attack. It's a classic. This is OS command injection, one of the oldest tricks in the book. It's got an official name and everything, CVE-2025-14558. It's what happens anytime you let data from an untrusted source get mixed up with commands that are going to be executed. It's a foundational security mistake. And don't think for a second that just because it's an old type of flaw, it's not a problem anymore. Just look at this data from recorded future. In August 2025, CVW78, this exact class of vulnerability, was the #1 most exploited weakness out there. The basics, the fundamentals, that's what attackers are still using day in and day out to successfully compromise systems. Which leaves us with this final, kind of thorny question. Think about it. The feature at the heart of all this, Slack, it was created to make our lives easier, right? For convenience. But that convenience introduced complexity, and it created this tiny crack where trust between 2 system components just completely shattered. So, when convenience and complexity collide like this, who's actually responsible for trust? Is it the developer who left that to-do comment in the code? Is it the system administrator who deployed the server? Or maybe it's the person who designed the protocol in the first place, prioritizing ease of use over security. There's no easy answer. It's definitely something to chew on.